Good morning, everybody. Hope you're all healthy and safe at home. So today we are going to move on to our new section 6.4 of the second module, and in this section we shall be discussing the concept of ortho projections and projections. So first of all, we'll understand the definition of projection, and with the help of this ortho projection is actually a extension of projections. So let's see the definition. Let E be a linear space. The operator P from E to E is said to be a projection if and only if P square is equal to P. Okay, so the operator, it is a property of a linear operator. That operator is said to be a projection if P square is equal to P. Now in this lecture we shall be discussing few properties of this projection. Okay, we shall see one by one. So first property is that for all x element of E1 we have P of x equal to x. That is P when restricted to E1, where E1 is nothing but the image of P. Okay, P is an operator from E to E, and we can find a set image of P. So P restricted to E1 is it will give the element of E1 itself, that is P of x is equal to x. That is true for every projection. So let's see, the proof is very simple. Let's see how we can do it. The first property, that is P when restricted to E1 is E1 itself. So for that, P of x, let us suppose that x is an element of the image of P. Okay, if x is an element of image of P, then there exists a y such that P of y equal to x. Right, there exists a y such that P of y equal to x. Now P is a projection, right? So P of y will be same as P square of y, right? So P of y and P square of y are same. Now what is P square of y? I can write this P square of y as, from this P of y is x, so if I apply P on both the sides I get P of, or I can write this as P of y, so this is nothing but P of x, right? So I get P of y is x and P of y is also px, so therefore I get px equal to x. Such a simple property to prove. So it is just saying that for every element in the image of P, what can we get? We can get that the corresponding when the projection acts on this particular element, we get the same element itself. So it is P of x, P acts as a identity operator in case of elements in the image of P. So this was our first property. Now we shall discuss the next property. The next property, it is about we shall be discussing about another projection, or with the help of P we can form another projection, that is Q equal to I minus P will also be a projection. If P is a projection, then Q equal to I minus P is also a projection, and also image of P and kernel of Q will be same, and image of Q will be equal to kernel of P. Okay, so let's see the proof of this. Again, the first one is pretty much simple. You just have to verify whether Q square is equal to Q. That is the property of the projection. So we have Q is equal to I minus P. So Q square will be equal to I minus P whole square. Let me just expand this, that is I square minus 2P plus P square. Now P is a projection, so P square is P itself. So this I square is I minus 2P plus P, that is again I minus P, which is equal to Q. So we get Q square is equal to Q. Therefore Q is a is a projection, right? So we get that Q equal to I minus P is a projection. Now next, what do we need to prove? We need to prove that image of P and kernel of Q is same, and image of Q and kernel of P is same, right? So first, let us suppose that X is an element of image of P. Okay, this implies there exists a Y such that P of Y equal to X. Okay, or by property 1, also by property 1, if X is an element of image of P, what is the first property? P of X is equal to X, right? So let's see what is Q of X. Q of X will be nothing but I minus P of X. This is equal to X minus Px. Now Px is X, so X minus X is 0. So Q of X is 0. This implies X is an element of kernel of Q. So image, if we take an element in image of P, we get that it is an element in kernel of Q, and so therefore I can say that image of P is contained in kernel of Q. Now let's see the backward implication. Let us suppose let X be an element of kernel of Q. Okay, this implies I minus P acting on X will be 0. This implies X minus Px equal to 0. This implies X is equal to Px, and therefore X is an element of image of P, again by first property. So therefore combining these two, from this I get kernel of Q is contained in image of P, and we have proved the other inclusion also, and thus we get kernel of Q equal to image of P, right? And the other portion, that is kernel of P is equal to image of Q, can also be solved in a similar manner. It's just, we just have to use the first property to prove the second property. That is, first property states that our P of X is equal to X for every X element of E1. E1 is the image of P. So the second one is also, you can prove it in a similar manner. Just take an element in the image of Q, and image of Q means you can, using first property, you can say that Q of X is equal to X. So I minus P of X is equal to X. So this implies X and P of X are same. So from that we can easily find that that is an element of kernel of P also. So the proof is similar. So now let's see the next property, which is about the direct sum. That is, E1 is the image of P and E2 is denoted as the kernel of P. Then the space that we had treated, that is E, will be nothing but E1 plus E2, and also E1 intersection E2 is equal to 0. Okay, so that is, the linear space can be expressed as the linear space that we have considered can be expressed as the direct sum of image of P and kernel of P. Okay, so that is the third property that we are going to discuss. So let's see how we can prove this. So for that, E1 is nothing but image of P, right? So E1 is equal to image of P and E2 is equal to kernel of P, where P is the projection from E to E, right? Okay, so clearly E1 will be contained in E, right, because image of P is contained in E, and E2 is kernel of P. By definition, E2 is also contained in E. So therefore the set E1 plus E2, what is E1 plus E2? That is nothing but X1 plus X2, where X1 is an element of image of P or E1 and X2 is an element of E2. Okay, this will also be contained in E, because E is a linear space, so the linear combination will also be contained in E. So that is clear. So this one inclusion is clear. Now let's consider, or let's see the other part. So for that, let me choose an element. E belongs to the linear space E. Now E can be written as E minus P of E plus P of E, right? So this is nothing but I minus P of E plus P of E. Okay, so I minus P was nothing but Q, right? Q of E plus P of E. So this is image of Q plus image of P. This is an element. It belongs to image of Q plus image of P. Now just now, the second property we had seen that image of Q is nothing but kernel of P. So this is kernel of P plus image of P. So any element in E can be written as the sum of kernel element, can be written or expressed as the sum of element in kernel of P and image of P, that is E1 plus E2 again. Therefore combining we get E is nothing but equal to E1 plus E2. Okay, now we need to show that it is a direct sum. So for that we need to prove E1 intersection E2 is equal to the set 0. Okay, so for that let me choose an element x in E1 intersection E2. So it is enough to prove that x is 0. So x is an element of E1 intersection E2. This implies x is an element of E1 and x is an element of E2, right? Now if x is an element of E1, E1 is nothing but our image of P, right? So x is an element of E1 means P of y is equal to x. There exists some y such that P of y is equal to x, and x is an element of E2. E2 is kernel, so P of x equal to 0. Now let's take this portion, this equality, that is P of y is equal to x. Now P of y equal to x implies P square of y, I am applying P on both the sides, is equal to P of x, right? This implies P square, P is a projection, so I get P of y is equal to Px is nothing but 0. P of x is 0 because x is an element of kernel also. So this implies x is equal to 0. So I have chosen an arbitrary element in E1 intersection E2 and I have got that x is 0. So therefore we can conclude that E1 intersection E2 is nothing but the set 0 itself. Okay, so this was the third property that we had discussed about the projections. So let's see what is the next property. The next property it tells us about the another operator and the commutativity of the projection and this particular operator. That is, let's see, let T from E to E be a linear operator, let E1 be image of P and E2 be kernel of P, the same as in the previous property where P is a projection. Then TP equal to PT, that is they commute, these two operators commute if and only if E1 and E2 are invariant subspaces of T. Okay, so we can say that an operator and a projection, they commute only if they are the corresponding image and kernel of the projection operator is invariant under T. Okay, so let's see how we can prove this property of the projection. So first of all, let us suppose that we have to prove the property. So suppose TP equal to PT. Now we need to show that T of E1 is contained in E1, then only E1 is an invariant subspace, and T of E2 is contained in E2, right? So I'm choosing an element in E1. Let Y belong to E1. Now what is E1? E1 is nothing but image of P. So this implies, as Y is an element of image of P, there exists X element of E such that P of X is equal to Y. Okay, so now let me see what is T of Y. T acting on Y will be nothing but T acting on P of X. This T of P acting on X. TP and PT are same. P of T of X. Okay, so this is again an element of the image of P, right? If I choose this element, say I write this as W, so P of W is an element of image of P, so I get T of Y is an element of E1. So when Y is an element of E1, I get T of Y is an element of E1. Therefore T of E1 is contained in E1, because I had chosen Y arbitrarily. Now similarly we can see what is the case of E2. Okay, so let me choose an element X in E2. Now E2 was nothing but kernel of P. So if X is an element of E2, kernel of X, sorry, not kernel of X, P of X will be nothing but 0. Now P of T of X is nothing but PT of X, right? So this is again T P of X, this is T of 0, and this is 0. So I get P of T of X is equal to 0, right? P of this element is 0 implies T of X is an element of kernel of P, right? So I chose an arbitrary element in kernel of P and I got that T of X is also an element of kernel of P. Therefore T of E2 is contained in E2. Okay, so I get E1 and E2 are invariant subspaces of T. Now we need to prove the converse part, that is conversely suppose that E1 and E2 are invariant subspaces of the operator T. Okay, that is what does it mean? T of E1 is contained in E1 and T of E2 is contained in E2, where E1 is image of P and E2 is kernel of P. We need to show that TP equal to PT, that is these operators commute. Okay, so for that, let Y be an element of E. Okay, now we know E can be written as E1 plus E2. We had just now seen in the previous property, right? E can be written as E1 plus E2. Therefore Y is equal to Y1 plus Y2, where Y1 is an element of E1 and Y2 is an element of E2. Now Y1 is an element of E1. This implies there exists an X1 such that P of X1 is equal to Y1, and Y2 is an element of E2 implies P of Y2 equal to 0. Okay, keep these things in mind. Now let's see what is PT of y. Okay, this is nothing but pt acting on y1 plus y2. So this is p of t of y1, both are linear, right, plus t of y2. Okay, now this again p is linear, so p of t of y1 plus p of t of y2. Okay, now y2 is an element of E2. Okay, and we have assumed that E2 is invariant under T. So y2 is an element of E2 implies y2 is an element of T of E2 also, right? So this is actually an element of E2. So this implies P acting on E2 will be 0. So this term is equal to 0. Okay, so I get this is equal to P acting on T of y. Now again E1 is invariant under T, so T of y1 will again be an element of E1, that is T of y1 is an element of the image of P, and P when restricted to image of P we get it as T of y. That was the first property, right? P acting on elements on E1 is nothing but that element itself. P of x is equal to x. So P of T of y1, T of y1 is an element of E1. So I get that is equal to T of y1 itself. Okay. So I get Pt acting on y is nothing but Ty1. Now let us see what happens to Tp acting on y. In a similar manner we can obtain that. This is nothing but T of P of y1 plus P of y2. P of y2 is nothing but 0, so this is T acting on P of y1. P of y1 is an element of image of P and T is invariant, so this I can write this as T of y1 or P of y1. Y1 is an element of image of P, so P acting on y1 is y1 as well, so this is T of y1. Both are same, so I get Pt acting on y is equal to Tp acting on y for every y. Y was chosen arbitrarily, hence I get Pt equal to Tp. Okay, so this is how we have proved the commutativity of an operator and the corresponding projection. So these are the 4 properties that we are going to be discussing in today's lecture. First was what is a projection, then we showed that P acting on E1 is E1 itself, then we showed that, and we can find another projection which is I minus P, and their image and kernels will be same, and we also showed that the linear space E can be expressed as the direct sum of image of P and kernel of P, where P is the projection. And finally the last property, that is when we are considering any operator, any linear operator, and the projection operator, we can say that they are commutative if the corresponding image of the projection and the kernel are invariant subspaces of the linear operator. So that's it for today's lecture. So just go through all the properties of projection. So thank you, stay safe, stay healthy.